Let's do mystery toggles now. We finally did it. Like, we're finally ready to like analyze a real algorithm that's actually doing something. So let's do it. Well, let's not quite do it, because mystery toggles, you know, okay, let me remind you about mystery toggles. Mystery toggles was some crazy programming task thing where there was like a mystery subroutine called mystery toggles, which may or may not have like a bunch of instructions like if x1 then toggle ants, if x2 then toggle ants, if x3 then toggle ants, and so forth. And you like tried to figure out which ones of these instructions it had by calling this subroutine as few times as possible. And we saw like this miraculous quantum algorithm that could figure out like the entire contents of mystery toggles with like a single call to mystery toggles using the magical power of quantum computing. And now we're going to try to see how that's working, if not really the deeper why it's working. But it's going to be very painful to do it with like all 6 variables. I mean, you can do it with any number of variables, and it gets actually cooler and cooler like the more variables, the x's there are, because you know there could be 100 x's, and still quantum can figure out all of mystery toggles with like one call. But let's do it with 2 x's, just because, okay, I don't want to write a billion symbols on the board. So we're going to do it with like 2 x's, x1 and x2. Okay, and ants. This answer qubit. So we're going to analyze the mystery toggles where there's 3 total qubits, x1, x2, and ants. Okay, so I will now write down all the code. So really, I'm writing down, well, I'll write down the, you know, detective code. So it looked like this. So 1, we got to initialize these 2 qubits on new qubits, x1, x2, and answer. And if you remember, the very first thing you do is toggle answer. And again, at the end of this lecture, you'd be like, why did they toggle answer? Like, I don't really understand. We'll eventually get to that. That'll be the goal of like the next few lectures, to understand like why this code is the way it is. But today we'll just see what it is. The next instruction was like, well, we called it at the time Hadamard all. But really, this was just shorthand for like doing Hadamard individually on all the qubits in the world, of which there are 3. So we could write like Hadamard x1, Hadamard x2, Hadamard ants, but now let's not do that. Let's do add and diff, because it's more nice. So will this is be add and diff on x1, add and diff on x2, and add and diff on ants. Okay, then the next thing we did was, this is where we made the call to mystery toggles. Mystery toggles, if you will. And this over here, you know, there's 4 possibilities for it. You know, it might have if x1, then toggle ants. And it might have if x2, then toggle ants. But also, like, maybe potentially some of these are, like, you know, commented out. So, like, any subset of them could be commented out, and therefore, like, there's 4 possibilities for what it could be. Okay, then the next possibility, or the next thing we did was we did Hadamard all again. And I'll write that in a second, but, like, the last thing was when we printed. That was extract all. And again, we're going to change these Hadamard all, which is really 3 Hadamard instructions, to these add and diffs. Now, I'm going to actually do them in the opposite order. And actually, this may raise a point to you, which is that, like, is it the same if you do, like, if you change the order? And depending on how far you've gotten on working on the homework, you might be more or less comfortable with the statement I'll make, which is that it doesn't matter the order. So it turns out to be like a principle of quantum computation that just mathematically follows really easily from analyzing amplitude trees. That if you do like an instruction on some qubits, and then you do another instruction on a different set of qubits, then you get the same results if you did the instructions in the opposite order. It's like you can parallelize them. Like physically, you can do the one instruction on these qubits, and these other qubits, you're not touching them, so at the same time, you could be doing the other instruction on these other qubits. If they're not overlapping sets of qubits. You could do that in physical real life, and therefore, like, it kind of better be the same, that it doesn't matter the order in which you do them. And, you know, if you did part of the homework, you'll see, yeah, it doesn't matter the order that you do them. And therefore, you know, when you say Hadamard all, you don't even have to say what order you're doing them in, because the order doesn't matter. And so I want to do them in this order here, because, like, it's the opposite order. And it's kind of like you're reversing, this block is like the reverse of this block. Okay, so this code has like, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 or 11. It has a lot of instructions. So we kind of want to analyze all these instructions. So we need like a bit of a system to do this effectively. And also remember how it's supposed to work. If you remember way back, the whole excitement of this is when you do extract all, it turns out like, it'll print 3 bits, like 0, 1, 0. This one is answer. Well, actually, answer will always come out 1, so you just ignore this part. But like these 2 bits, like tell you what's in mystery toggles. If you remember, like if this is 0, 0, it means like both lines are not appearing. If this is like 1, 1, that's when like both lines appear. If this is like 1, 0, it's like the first line is in there, x1, and the second line is not in there, and so forth. So this is what we're like shooting for, trying to understand why this happens. Okay, so let's kind of get started. Well, you'll see like right away, like we're going to need some kind of good system to keep track of things. So okay, when we do the new qubits, we'll just be in the basic state 0, 0, 0. That's how it works. And the first thing we do is toggle ants. So then we're just in the basic state like 0, 0, 1. Okay, so after line 2, everything is pretty easy. Like after line 2, the state is just literally 0, 0, 1. Okay, I'm always going to write them in the order x1, x2, then ants. Or more fully, you would say, amplitude 1 on 0, 0, 1, and amplitude 0 on the 7 other basic states. And now we start doing like these like add and difference operations. So we need to get organized. And as we're doing these, we're always going to have like 8 amplitudes we're keeping track of. One for all the 8 possibilities. So we need like a system for like depicting 8 numbers. Okay? So we're going to draw them on the corners of a cube. Okay? So this is my life pro tip for you. This is not, again, you don't have to do this. This is, again, just a mathematically convenient way to organize your thoughts. But my tip is that, like, if ever in analysis you have up to 3 or 4 qubits, it can be very helpful to arrange them, like, in a cubical pattern. So I'm going to draw this picture like this. Okay, let's draw like a 3-dimensional cube. Make this bigger. Hopefully I can do this. Okay, let's try to put the lines in. Oh, shoot. Oh, man. Okay. Okay, that's a 3 by 3 cube. It's impossible to tell, but like try to in your mind like visualize it so that like this is like the front and like this one is the back. If you can make your brain do that. Now, why do I draw a 3-dimensional like a 3-dimensional cube? It's because we have 3 qubits, and each qubit is associated with a direction. So I'm going to use these directions. Let me draw this like legend in the corner. We have up and down, and that's going to be associated with x1. We have left and right. That's going to be associated with like x2. And we have like in and out, and that's going to be associated with ants. Okay, so like, and moreover, like this is going to be like 0, 1, 1, 1. So what I mean by that is like here, like this corresponds to 0, 0, 0. Just like ants is 0. Sorry, x1 is 0, x2 is 0, and ants is 0. Okay? And like as I draw these, in your mind, like try to also simultaneously figure out what string I'm going to write here. So like this is x1 is on the bottom, it's like 1, 0, 0. And this one is 1, 0, 1. This one's 0, 0, 1. Maybe I should intentionally make a mistake and you try to fix the mistake. 0, 1, 1, 1. 0, 1, 0. Okay, what mistake did I make? Oh, so good, yes? Yeah, you're right. I tricked you. This is 1, 1, 1. This is 1, 1, 0. Okay. You might ask, like, oh, why is x1 like the up and down and x2 the left and right and ants is in and out? Doesn't matter. I just picked that. That doesn't matter. You can draw it however you want. And like y is like 0 on top and 1 on the bottom. Doesn't matter. I just picked 0 on top, 1 on the bottom. But you know, it's important that the 3 qubits are 3 different directions, and like there's a 0 side and a 1 side. Okay? So this depicts all the basic states, and let's write in the amplitudes for where we are. So right now we're here, and we have 1 amplitude on 0, 0, 1, which is somewhere here. 1. And we have 0 amplitude on everything else. So let's just write zeros, okay? 0, 0, 0, 0, 0, 0, 0. Okay, so it's kind of a crazy diagram, but like this diagram is illustrating our current state. And like as we go along, these red numbers, which are the amplitudes, will change to different numbers, and like it's indicating what state we're at. Okay, but this I hope will help us. Any questions? Okay. Okay, so basically I will like update this diagram as we like trace through all the lines of code. So like we kind of did this one and we did this one. So like now we're on this one. Add and difference on x1. Now how the heck does this work? Well, remember when I was like, if you're doing like Hadamard on 1 qubit, but there's like several qubits, how does it work? We had this diagram up here where like you paired the basic states up. There was like red and green. You pair the basic states up according to the unchanging part. Okay? So add and difference of x1, we're operating on x1, so the unchanging part is x2 and ants. So we have to like pair everything up based on where x2 and ants are the same. So let's take a look. Here in color, green, I'll like underline the x2 and ants part. That's the second 2 qubits. And actually, these two match up, right? Because these are both 0, 0, 0, 0. So like this edge, if you will, or this pair of basic states, this corresponds to like the world where like x2 is 0, ants is 0. So we just like forget those ones are both 0, and we have like 0 and 1 for x1. And we're going to do add and difference on it. Okay? So how does add and difference work? Well, you put the sum of the amplitudes on the 0 part, and you put the difference of the amplitudes on the 1 part. Now here it's boring because the 2 amplitudes are 0 and 0. So their sum is 0 and their difference is also 0. So we don't actually have to change anything here. The more interesting pair is this one. Like this is the interesting pair. So this is like the world where the unchanging part, x2 and ants, is 0, 1. So everything there, they stay 0, 1. But here we have like amplitude 1 on the 0 part here, and amplitude 0 on the 1 part here. So these two get paired together, and we put the sum on the 0 part and the difference on the 1 part. So the sum is 1 plus 0. So, well, actually that stays 1. But the difference is 1 minus 0. The difference of 1 and 0 is 1. So this becomes 1. Okay, I just like did this pair. Is that clear? Now, you kind of see it's always going to be the vertical pairs. Like these two pair up because you end with 1, 0, 1, 0. You have 0 up here and 1 down here. And the sum of and difference of 0 and 0 is just 0 and 0. And similarly, these stay 0 and 0. Okay? So we did this step. Is that okay? You might be like, I a little bit forget like how this corresponds to the amplitude trees. But it does. You know, maybe it's good for you to review it. But like, eventually we're just going to maybe even forget a little bit. It won't be top of mind how we got to here from amplitude trees. But we'll be doing it in this way instead. Okay, so now we got to do add and difference on x2. So it's the same thing. Now x2 is like what we're operating on. x1 and ants are unchanging. So we like pair up all the basic states according to like x2 is the changing part and x1 and ants are the unchanging part. And we do the add and difference on all these pairs. Okay, so now x2 and ants, that's like the first and the third. Okay, so let's just pick one of them. Let's say this one. So here's the first, x1 is 1, ants is 1. Here's its pair where x1 is 1 and ants is 1. But like, you know, you have 0 over here and 1 over here. So these two are a pair. And we do add and difference on that pair. So, well, the amplitudes are 1 and 0. So the add of that is 1. And the difference of that is 1. So we write 1 here. The 0 part gets the sum. And we write 1 here because the 1 part gets the difference. And I hope you can see that, like, for this x2, we'll always be operating in the x2 direction. So we kind of pair things up according to, like, horizontal, and we do add and difference. So, like, here, we do add and difference on 0 and 0. That actually doesn't change anything. Here, we do add and difference on 0 and 0. That doesn't change anything. And here, we do add and difference on 1 and 0, and that becomes 1 plus 0 is 1. 1 minus 0 is 1. Okay, now we've done this step. Is it okay? Okay, now let's do add and difference on ants, the ants direction. So again, we pair the basic states up, and it's going to be pairing in the answer direction, so like the in and out direction. So, for example, here's 0, 0, 0. x1 and x2 are unchanging, so it gets paired up with this one where x1 and x2 are unchanging, and we have, you know, ants is 0 here and ants is 1 here. So we're going to be doing the add and difference of 0 and 1. Okay, so the add and difference of 0 and 1, 0 plus 1 is 1, and 0 minus 1 is minus 1. Okay, the one side gets the difference. So again, you know, we're going to be looking at all the edges in the in and out direction and doing add and difference. So 0 plus 1 is 1. 0 minus 1 is minus 1. In this direction, we have 0 plus 1 is 1. And 0 minus 1 is minus 1. 0 plus 1 is 1. 0 minus 1 is minus 1. I can easily make a mistake when doing this. So please, again, if I make a mistake, you got to let me know. Let's see if it checks out with my, yes, this checks out with my notes. Okay, so this is good. Actually, let me like pause. This is like after line 3C. Okay, like all the basic states on the back face have minus 1. All the basic states on the front face have plus 1. So we definitely have an unnormalized state, for example. The sum of the squares of the amplitudes right now is, well, every squared amplitude is 1, so their sum is 8. And the reason that the sum is 8 is because we kind of ignored like 3 copies of square root a half. Had we put those 3 copies of square root a half in, some of the amplitudes would go down by, some of the squared amplitudes would go down by an 1/8, which would put us back to 1. But that's annoying. We don't do that. We just stick with this. Okay, so now mystery toggles. So in principle, like, we should now break into 4 cases for like all the possibilities for like what this could be and check that the right thing happens. Obviously, I'm not going to do that. We have time to do like 1 or 2 cases. And then I will be like, oh, I leave the remaining cases to you. But let's do the easiest case. Case 1, mystery toggles contains nothing. I want to do this case because I can do it in words. How do I do this in words? Well, let's say you call mystery toggles and like both lines are commented out, so nothing happens. So now in principle, you'd be like, okay, now we got to just do this line, this line, this line, and check out what we get to. But here, like an interesting thing happens. Particularly if you remember that these are really Hadamards under the hood. And as we saw, Hadamard is its own undo. Hadamard is its own undo. So in your mind, if you think of these as Hadamards, we just did Hadamard on ants. Now mystery toggles didn't do anything, so the next instruction is Hadamard on ants. So like this line undoes this line. And then we did Hadamard on x2, so this line undoes this line. And then we did Hadamard on x1, so this line undoes this line. So doing these two Hadamard alls in a row when mystery toggles doesn't do anything just literally undoes itself. So like it's as though nothing happens and you've jumped straight from line 2 to line 6. So then what is that? Well, we know after line 2 you're in the state 0, 0, 1. So when mystery toggles is empty, this does some crazy stuff. This like undoes all that crazy stuff, and you're back to 0, 0, 1. And that's exactly what you're supposed to be back to. Remember? Like, remember I wrote it? I don't know if I wrote it. The way this whole game works is like this one will always be 1, but like these two tell you the contents of mystery toggles. And indeed, it checked out. Like 0, 0, because none of them were in there. So like that's how that case works. Cool.